maybe recap a little bit. Okay, so we're kind of motivated by this idea of fairness, okay, specifically in terms of how our decisions should be independent, perhaps, of, let's say, a sensitive variable like race, if we knew the quality of the candidate. So in this particular case, if we were going to know that somebody was going to commit a crime, then we wouldn't release them, no matter whether they were black or white, okay? And this kind of measures this. Or you can think about it the other way around. You can say, okay, that your, let's say, given your decision, given your decision, the actual likelihood should be independent of the race. Here it's the other way around. Given the outcome, your decision should be independent of the race. But these are all types of conditional independence. And the classical way to represent conditional independence in a model is through what is called graphical models in general. And more specifically, we talked about directed graphical models, directed acyclic graphical models. So they have no cycles. And these are also called Bayesian networks. Yeah. But I don't call them Bayesian networks because there's already lots of Bayesian things. So simplest to say just directed acyclic graphical models. Then that's another type of model where you don't have directed edges. They are undirected graphical models, and you can express slightly different types of dependencies between variables for those models. They're specifically interesting when you are, let's say, modeling an image. So pixels are neighboring. They probably have correlated values in some way, but you cannot say that the value of this pixel determines the value of the next one. Yeah. And then you could even use them, let's say, to describe textures, describe bigger elements in a picture. And so these have been very successful in the last 10 years before the neural network revolution again came. These were the most successful models for image analysis. Okay. Okay. But we are specifically interested in this idea because we would like to talk about how we can formalize the idea of conditional independence in terms of a simple model. Okay, so we mentioned the idea of that dependence changes when we know something compared when we don't know something. So in the large cancer example, if we don't know whether somebody has cancer, then the probability of smoking and the probability of inhaling asbestos are independent. But if you know that somebody has cancer and you know that they don't smoke, then it's probable that they have inhaled asbestos. And the other way around. It's like you're eliminating one possible explanation and the other one has to be true. Yeah. And the other way around for when you arrive at work, well, me and you might appear to be always late together, always early together, but if you know whether or not there's a traffic jam, you can just explain our behavior by that. So then we become independent. Okay? So that's the basic idea. And then these dependencies usually create, if you are trying to study data of some type, this creates some correlations which can be hard to explain if you look at the data in the aggregate. So this is what we saw with the treatment effects. Have a better treatment all the time, but if the worst treatment is assigned to the easier cases, then it might look as though the worst treatment is overall better. Okay? Okay. So there are a bunch of examples. So in terms of fairness, probably what we would like to know is maybe whether something is independent of something else. So, for example, this is not one of the two definitions we had before, but an alternative definition is to say that your action should simply just be independent of the gender, okay? But maybe it's not good because maybe all females are better, right? So you should accept more females. But let's say that this is what you want. You want your actions to be independent of the gender given the school. So in that case, you should have a way to distinguish between those two models. So in one model you have a dependence, and in another model you don't have a dependence anymore. Okay? So how can we distinguish those two models? Okay, first of all, we have to go all the way down to deciding what the model is for a specific case. How do we parameterize it? What is the distribution? And everything. We cannot just say, well, this is the graphical model, it's either this one or that one. It's not going to be enough. Okay, we have to put values to the variables, have to give distributions to them. Okay. So, for example, if I start with this model here, right, all the variables are binary, right? So it's these two variables are binary, sorry, and this one is not, because you have 6 different schools. Yeah. So now the question is, what kind of distribution can we use to represent this graph? Okay. So typically, if you know exactly the parameters of these distributions, then this is binary, right? So we know a very simple model for binary variables. Anybody?
Bernoulli?
Yes, the Bernoulli distribution has only one parameter. It's higher is 1, it's lower is the probability becomes 0. Okay? So we can use the Bernoulli distribution to model this Z. Okay? That seems fine. Okay, and now things become a bit tougher when you consider S, right? But let's think about it. So Z comes from a Bernoulli with an unknown P. Okay, fine. Okay, let's call it C. It's fine. Now, what S is? S depends on Z, right? In some way. So, what do we mean by that? For every value of Z, S must have a different distribution. There are 2 values of Z, right? At 0 or 1. So we expect S to have a different distribution for each one of these. Now, let's say Z equals 0 and 0 equal male. Okay? So let's say Z equals 0, male candidate, right? Now we would like to have a distribution for S given that Z is equal to 0. S has a finite number of possible values, right? And well, there's a fixed probability. You can show there's a fixed probability for being accepted to a school given that you're male. It doesn't depend on who else was accepted before. And that would imply a multinomial model, which is the generalization of the Bernoulli to the K outcome case. So you have here 6 outcomes instead of 2. It's like throwing a dice with 6 different sides. Maybe one side is bigger than the others, okay, depending on who is actually applying. So if it's female, it's 1 dice. If it's a male, it's a different dice. Okay. If you know the probabilities of every side for every dice, then it's simple, right? You can calculate the probability of S given Z for every possible value of S and for every possible value of Z. Okay. So we can just say that there's another parameter, and how would you see the probability of S is equal to K given Z is equal to I. Let's call this one theta ik, or theta, yeah, theta ik. Let's write it also on the board. So the probability that Z equal 1, let's call this one P, okay, or 0. The probability that S is equal to K, that K possible values, given that Z takes the value I, let us call this theta ik, okay? So now this has the property that for every possible value of I, now we have 6 Ks, right? This has to sum to 1. Because the probabilities of every one of these schools for every gender has to be equal to 1 when you sum them up, right? Okay. So we have these parameters, and then the last thing that we need for the first model is another parameter value, which is the probability of being accepted given that you apply to a school, right? So it's probability of K equal 1 given that you have applied to the school K. Yeah. And this one, we can give another name for this variable, let's say phi. Okay, phi of K. Okay, we don't need another one actually, because the probability of A equals 0 is just 1 minus this. Okay, and for this one, we don't really need K6 of them, we need only 5 because the fifth one is 1 minus the others. Okay. Theta I6 is just sum of I equal 1, 5, 1 minus the sum. Okay, right? This should be okay with everybody, right? Okay. Now, of course, the problem is that we don't really have these probabilities, okay? What we have is an estimate of these probabilities from data. And we can try and find the best fitting parameter for this model and also for the other model. Now, for the other model, it's a bit more complicated because this thing is not so simple anymore, right? These things also depend on the gender. So this is model 1, model 0, and this is the alternative model, model 1. Here we have the probability of being accepted depends on 2 things, right? The school, okay, and the other thing is the gender. Okay. Okay. This is the other model. So it has, this one has 6 parameters, and it has 12 for this variable. Okay. So this model 1 here. Okay, and then slightly different for the other model. Okay. Okay. So then the question is, how do you compare these models given the fact that they are different, they have different number of parameters, right? So the typical thing that we do is we use this idea of Bayesian comparison. You don't have to do that necessarily. One other thing you can do is that what we did very quickly in the code was we basically calculate model 1, and then you see, and then this model as well, and then you see if these probabilities are close. Yeah? If the probability of A equal 1 given only S is very similar to the probability of A equal 1 given S, Z taking different values, then it's probably difficult to distinguish them also. Even though you're not really sure if it's really independent, it seems as though it's maybe independent. Okay? So it doesn't give you a clear probability, yeah, it's independent, or no, it's not independent, or it's independent with 90% probability. It just gives you some indication of how much the dependency might be. Okay, this might be enough, specifically if you think about fairness, because we know that in practice we can never achieve perfect independence, so we just need some measure of independence, and then we would like to say that we want to maximize the number of, let's say, the utility that we have, but at the same time minimize the amount of deviation from independence, and we can measure this deviation by subtracting these two probabilities. Let's go through it a bit more. Okay. So how do we do it? Well, so if we are independent, then this should be equal all the time, which means that these also should be equal for any value of these variables when we change it. So one way to basically see if our model, however we calculate it, satisfies independence approximately, is to look at this difference. In the particular case of fairness, you have the action variable, the quality variable, and the gender or race variable. And then if this difference is small, then the model is nearly independent. It's maybe not perfectly independent, but for practical purposes, it might seem independent. Okay. In fact, you can just use this as a metric to say, okay, if it is large, it's bad. We want this to be as small as possible. Okay. Because in practice, we might never be able to do this. In fact, if we actually have a fully Bayesian model of this, right, then we can think of this as the reality. So we really believe in our model, and then what deviation we measure is actually the expected deviation from fairness. So we'd like to minimize expected deviation from fairness according to this equation, and at the same time maximize our utility. We'll go through that a bit later. But basically the computation says that for every possible value of y and z, take the maximum over these possible differences, And here, this is just the L1 difference between these two distributions. Yeah, so these are two different distributions for A, because one is only conditional on Y, and the other is conditional on both Y and Z. So you have two different multinomial distributions in this case, or two different Bernoulli distributions. And it's pretty simple to look at the difference. It's just phi k minus phi k j absolute value, sum of all the possible k's, all the possible a's. Here there are only two a's, so it's this one and 1 minus this one. Okay, so it's pretty simple to just measure it. But okay, what if we actually want to make a proper inference about is it independent or not? Okay, so we're going to talk a little bit more about how all this graphical model idea also fits back into the idea of Bayesian inference. We saw before that in Bayesian inference we basically have a finite or an infinite set of models. We have a prior probability for every possible model, and then given the data we can get a posterior probability. If you formalize this as a graphical model, you can do it as well. It doesn't make a difference. Let's take the coin tossing model, right? So for the coin tossing model, you assume there is a coin whose distribution of heads and tails is governed by some Bernoulli law, yeah? With some unknown parameter theta, let's say. Yeah, theta takes values between 0 and 1. Now, the thing is that we don't really know what theta is, so we assume some prior distribution xi, okay, or parameters of a prior distribution xi. Now, given a value for xi, for this prior distribution, then there is a fixed distribution for theta. Okay, and given a theta, there is a specific distribution for the data x that we see. Now, the interesting thing is that when we are doing inference, what we're actually trying to do is we know this guy because this is the parameters that we select for our prior, and these are the data. And what we're trying to calculate is the probability distribution of this one given our prior parameters and the data. Okay. And typically, what you do when you write this type of model is you can write it in this form by written. So here you actually specify what the distribution is. So here we say that theta is coming from a distribution beta with parameters xi1 and xi2, and that if you know theta, then your x is distributed according to a Bernoulli distribution with parameter theta. Yeah. So in that case, it's independent conditionally of xi. Yeah. So this notation is a bit similar to the conditional independence notation, and we basically use this to describe our models. Okay, so let's go a bit here. Now, doing inference with arbitrary models like this is difficult. Okay, so let's see. For that reason, we are going to take a look at a package called PyMC. Okay, so there's quite a lot of stuff here. Now, this is an interesting package. Basically, it uses standard notation, like similar to the notation I described, for specifying a graphical model. Yeah? It tells you what the different distributions are. You tell it what the different distributions are and how the variables depend on each other. And then afterwards, you can actually do any inference you like, pretty much, with it. It's a very general package. Yeah? And if you want to do anything with graphical models, then right now this is the only thing in Python that is actually mature, that you can actually use. Okay? So how does it work? Well, this is a linear model where there's a dependence between different variables, but some of them are independent. So here I have alpha and beta are independent variables. And there's another variable which is mu, which is the sum of alpha and beta and x1 and x2. Okay. Now the interesting thing is that the observations themselves are generated from another normal distribution, right? Which has a mean that is equal to this one, so there is now dependence, right? So now the distribution of y is dependent on the values of alpha and beta, which also have some other distribution. So basically, it's kind of similar to what we said. We'll say that x given y given x here is normal with a mean dependent on x. Like we said in our example, x is distributed Bernoulli with something that depends on theta, and theta itself has a beta distribution. So here it says alpha has a normal distribution, and beta has another normal distribution, and then this mu thing is the sum of those things. Plus now the y is a normal distribution again, but the mean of this one is basically a random variable as well, and depends on these ones. Now there is a lot of stuff you could play here, and okay, what was it again? And a lot of methods you can use, but you basically can use it to estimate mean and variance of a Gaussian distribution here in this example for your means. It's pretty interesting. So here you see the standard notation I was using as well, right? So you have one random variable here and another one here, and then this one actually depends on this sigma, what we randomly generated, okay? And this SI here depends on the previous SI, so it's like a sequential model. And you can also fit it by basically doing the same thing. So you say nu is exponential, sigma is exponential, and then there's a special thing for random walk here, because this is a random walk. Because this thing basically, it's a Gaussian random walk because it's a normally distributed variable whose next step is normally distributed with mean equal to the previous step and some fixed variance. Okay, so the only basic problem you have with this, it might be that you want to have some distribution to model between two variables that is not in there, and the second problem is finding what the distribution that you want to model. Right? So, because there are quite a lot. But in our course, we're only going to focus on beta Bernoulli and maybe Dirichlet multinomial. But as far as I remember, you don't really need to do that. Okay, I think in the example we have with the query data, beta Bernoulli is probably going to be enough. Okay, because we have binary outcomes and then binary decisions as well. And there are many different choices for what is the sensitive variable. You will find it, but there are many different choices. But you never actually care about the distribution of this variable. You only care about the distribution of the other variables conditional on that one. So you might not need to define it. But if you do, we can also mention it here. Okay, so this is basically just an overview of the package at a very high level. There are more examples, but before we go to more examples, let's continue a bit with what the basic problem is and what you can actually do with this package, okay? Later. Okay, so we want to do some kind of inference, and the first step for inference is specify the model, okay? This is not just the graph itself, but the actual dependency between the variables. What distributional form do they have? And as we saw in this Python MC example, they do specify specific values. Yeah, so this has to be Bernoulli with this parameter, and everything has to be specified precisely. Okay. Even though everything is specified precisely, in fact, what you do is you precisely define how uncertain you are. Put it in this way. In what way you are uncertain, you have to specify exactly. Okay. Now, I'm making things more complicated, and I think I have to at this point. if we want to go to a bit more depth. But I hope that's okay. Yeah. So now we just have one coin, and we want to estimate the distribution, or what is the probability that the coin's bias is 0.5 or 0.6 or 0.7. We can do this with a simple Bethe-Bernoulli model. But let's say we don't care about the exact value, we just want to care is the coin really fair, or is it some other value? Is it 0.5 or is it something else? Yeah. So typically you do a simple null hypothesis test for that. But let's be consistent and use a Bayesian approach, because with a Bayesian approach you basically use always the same recipe. You don't change the recipe. You just say hypothesis 1, hypothesis 2, posterior distribution. That's all. Yeah. The only difficulty is calculating this posterior. And you have PyMC, you can do that. Okay. So now we have two different ideas. The first is we have an unknown Bernoulli distribution, possibly. And the second is we have an unknown model for this Bernoulli distribution. Let's say that model 1 is specifically for the case where we think that the coin is distributed with some unknown Bernoulli parameter theta between 0 and 1. So it could be unfair, or it could be perfectly fair. We don't really know. So we will just use the same idea. So when your model is equal to mu1, then we should use the same model as before, the same distribution for theta. However, when we define an alternative model called mu0, and for this specific model we say that the value of the Bernoulli distribution is always 0.5. It's the perfectly fair coin. Okay? Now we can represent this basically like this. We have one part of our prior or belief is defined by this parameter here, which tells us how likely we think it is to be perfectly fair, and how likely it is that we just get a randomly selected coin from this beta distribution. And this parameter xc basically tells us, okay, if we know that the coin is not the fair coin, then what's the distribution of possible unfairness or bias that the coin could have? Yeah. So the way that we actually write this is like this. If the model is equal to model null, then theta has a distribution that is deterministic and takes the value 0.5. I just use the symbol to say deterministic. You could use something else, but there is no standard, I think. Okay. The second one basically says, okay, if the model is model 1, then the distribution of theta comes from a beta distribution of parameters xc1 and xc2. Okay? So now this graph corresponds to the dependencies between all these variables here, right? So if we know phi and xc, then we can generate values from x by randomly generating a mu, and then from the mu randomly generating a theta, and then from the theta, of course, the theta's value has to depend on the xc1 and the xc2 as well, if it's mu1. If it's mu0, it doesn't matter. But if it's mu1, then it has to depend on xc. So then we generate theta, and then we also generate x. Yeah? So basically these lines just tell you how you generate new data. Okay, now if you have data, what you want to do is calculate the distribution of this guy specifically, the probability of every model, given your prior parameters and the data. You don't really care about the distribution so much, but you care about this one. Because this is a nice summary, because it tells you the probability of model 0 and probability of model 1. And this is the only thing you care about in the end. Okay. So, how do we use this idea to test for independence? You have two models. One of them assumes independence. Okay. And the other one does not. It's like what we had here. It's exactly the same thing. Yeah. Now, let's take the case where all the variables are binary. Okay. And so there are triplets. And we have for many tie steps from t equal 1 to capital T. And then for the first model where there's no dependence, we have, and for any possible parameter value for that model, okay, we have that the probability of the data is basically the product of these factors And its factor is basically the product of the probability of x1, the probability of x2 given x1, and the probability of x3 given x2. Okay? And for the second model, it's almost the same, but here the probability of x3 depends on the values of x1 and x2. Okay? So that implies that basically this parameter set, theta1, is different from this one. Yeah? Because here you have more parameters for this distribution. But the parameters that describe these ones are the same. Yeah? So it's basically analogous to this one. Yeah? So here we had theta I, k, phi k, and phi k, j. And here we had p. Now just to make it simpler, I just call everything theta. And then for every one of these sub-distributions here, I will define some parameters specifically. Okay? So let's go through it by one. So the first one, well, okay, it only has one parameter, right? Theta1. It's common for both models. The probability of x1 taking the value of 1. This one here, x2, only depends on x1 for both models. So we just have another parameter. Now here in the subscript, I use 2 given 1 because it basically tells you exactly what's the relationship this parameter describes. Okay, so now we have basically 2 values for this parameter as well, 2 parameters for this one. When x1 equals value 0 and when x1 equals the value 1. So 1 and another 2 parameters, it's 3 total parameters so far. And then here you have 3 given 2 for the first model. This is equal to another 2 parameters, so we have 2 plus 2 plus 1, it's 5 parameters for this model. But for that model it's more complicated because there is a dependency between x1 and x3 as well. Yeah. So now we have probability of 3 given 2 and 1 for for x2 equal j and x1 equal I. So all these combinations, there are 4 combinations, so there are 4 different parameters here. So it's now have 7 parameters for this model as well. Okay. So now the only thing that remains is to specify what is the distribution of the thetas before we see the data, so our prior. Yeah. Well, this one can be beta, this one can be beta, this one can be beta, and this one can be beta, because they are all binary. Yeah. They're all Bernoulli distributions, right? Parameters. So we can in fact use a product of 3 betas from the first one and a product of 3 beta distributions for the second one. When I say product, what I mean? I mean that there is no dependence between the parameters themselves. So if theta1 is 0, then this shouldn't affect what we know about theta2, 1. So we make these assumptions because we'll have no reason to believe that it can be otherwise. Okay? In some problems with the structure, we might say, okay, if the probability, if this one is 0, then this has to be 1. But we have no reason to do that, so we just say everything is independent. Okay? There's an obvious exception to that. If theta1 is my parameter, theta2 is your parameter, and theta3 is your parameter, and so on, we all come from some population where we are somehow related, maybe. So you could say that if my parameter is high, then your parameters should be high as well. But here, there's just some edges in the graph. We can't really say anything beforehand. So we just say that completely independent distribution for each one. Okay. So this is a basic model. We don't actually say anything. Here I remove all the extra edges. We have 2 so-called latent variables, which are the variables we don't know, the model and the parameters of the model. And the model comes from the prior phi, and the parameters of the model will come from the prior for the specific model. Now that we have the likelihood function here, so we know exactly what these are, just product of some thetas, right? Now we also need, because we want to calculate the Bayes rule, we need the marginal likelihood, so the probability of the data under any model. And if you remember, this is basically the probability of the first model times the probability of the data under this model, plus the probability of the second model times the probability of the data under this model. Yeah. Just to remind you the rule, it's basically PA is equal to P of A given X times P of X for all possible X's. Yeah, that's very well. So that's basically the same thing. And the second thing is the probability of the data under a specific model. Right? This is the same thing as here, just an integral, because you have an infinite number of possible parameter values. And here I'm integrating over the parameters that are valid for model I. So because each model may have a different set of parameter values. And we know it has to be different because this one has more parameters, this one has fewer parameters, so the spaces are different. So we are integrating over a different thing. But formally it's kind of simple. Yeah? Okay, so we have a formula for this, and then you put it in the posterior, right? So this is the probability of each model given the data, probability of data given under the model, and the probability of the model, summing over all the models. Okay, that's basically the same thing as this thing here, the denominator, right? So we're basically done, apart from actually calculating it, right? So calculating is difficult, and this is what we'll focus on, I guess, when after the break, maybe more. But typically we saw that to calculate the marginal likelihood, which is the denominator in the Bayesian calculation, when we did this weather example, we basically had a finite number of stations. Every station gave us probabilities. We had the probability of every station. You could just calculate directly, summing everything up together, right? Now we have an infinite number. Now we have models that are complicated, and for every model there's an infinite number of parameters. So if we want to really calculate this, then we have to calculate this integral. Okay? Okay. Now there is a theorem. I'll just go through it now, I think. Okay, so let's say that we have some function that is bounded between 0 and 1. Okay, then we know that if we calculate the expectation of this function, let's say that we want to calculate the expectation of this function, but we cannot, right? So this is the integral of f of x over the probability of x. Okay. Okay. Let's say what we want to approximate instead by sampling. So we take samples from x, from this p, and we calculate, let's say, nu hat n is basically 1 over n, sorry, capital N, sum n equal 1 to capital N f of xn. Okay, so we just average the values of the function. Okay, then there's a theorem that says that the probability that our estimate minus this expected value is going to be larger than epsilon, smaller than 2e minus 2n epsilon squared. Okay, so that means that the probability that we are more than epsilon wrong is exponentially decreasing with n. Okay, you can rewrite this a little bit in another way. Let's call this quantity delta. So now you can write delta 2 is equal to e minus 2n epsilon squared, and that means that ln delta 2
is equal to minus 2n epsilon squared, which basically tells you that epsilon is basically square root, right, ln 2 divided by delta, okay, and then 2 times n, okay. Okay, so this is what is called the Hofting inequality. And it's very useful because it holds all the time. And another interpretation of it is that you can think of it as saying that the probability that with probability at least 1 minus delta, your error, which is this difference here, is going to be smaller than this quantity. Okay. And this is basically what we have written here. We say that when we estimate an integral, we can approximate it very simply by sampling, and then our approximation error is guaranteed to go down the square root, no matter how many samples we take. This is not an asymptotic result. It holds for any value of n. Okay. Now there is this O there. It hides something, and this is because I mentioned this theorem. It holds for functions bounded between 0 and 1. Okay, you can scale it up. So if the function is between 0 and 1,000, then you basically make this epsilon factor 1,000 times larger. So basically, this thing will become 1,000 times larger. Okay, and this is kind of a problem because what is the maximum value that this can take? Right, it can be quite high. Actually, if you think about it, right, it depends on the model, but for some models, let's say a normal distribution with very low variance, like very close to 0, then for some data it can be very, very high, right? So it's annoying. And for that reason, it's not very efficient, actually. So even though your error rate goes down in a nice polynomial way, you're kind of messed up by the fact that there's the scaling factor in front because of the size of this. Okay, so I guess after the break we'll talk about some ways to fix that very briefly. Yeah, okay.